Hey, want to give you an idea of what to expect in terms of the AP exam for questions related to the lab. So I have three resources here, and you've got a quiz that's going to connect to practicing the things you need to know about labs that we did this year, maybe labs from the past, or kind of extensions of labs that maybe we didn't do yet. So there's a few different resources that I'm going to show you and highlight from. One is the NIMSI, National Math and Science Initiatives, lab-based questions. That's where we're going to focus most of our time and attention. I do have a slide presentation here. So to give you a really quick overview on that, these are the topics we covered more or less in this order. And we did labs related to many different things here. We did one where we were analyzing a mixture. That's one that was kind of a mix of in-person and virtual. Some precipitation labs, some titrations, the titration with the purple stuff. The reaction where we saw things doing thermo, getting hotter and colder. The purple fading away with kinetics. This one we didn't do this year, but you probably have done some version of that in first year chem, where we're changing surface area, concentration, and other factors to look at rates. We did a lab with Le Chatelier's principle, where we were seeing different shifts in equilibrium. Some more titrations where we were thinking about acids and bases. We did this virtually, but also connecting to what we maybe did in first year chem and just our discussions. We made a buffer and then we tested it. We didn't do this exact one. Rather than doing this one, and I'll talk about it, we did the thing at home with colorimetry, but it uses the same idea where we're looking at the color of a solution to know its concentration. We did do our unknown bonding lab where you had to figure out what was ionic, covalent, metallic, etc., based upon their properties. We did this one with the different gases that we heated up in the test tubes and tried to find their molar masses. For this, we used markers to find the different colors on the paper. We didn't do the pain relief mixture. That one we were a little bit short on time, but it was a similar idea to separating solutions, but using solubility and some other different things with polarity. And then we did do the combination of virtual and hands-on electrochem cell. So here I kind of summarize the process, the concept related to those things, and some notes to remember. You'll also see those in the other places. So then right here, these are some things I'm going to highlight as well. But this is a good document to kind of skim through, connecting specifically to what we did and kind of how we did it. Right here, this is a website that I'm going to ask for you to look at because it was written by a very good AP Chem teacher. This guy, Adrian Dingle, has been teaching AP Chem for much longer than I have and preparing kids for the exam very, very well. So he focuses mostly on teaching to the AP test or getting people ready to go. So that's kind of the tone that you'll see with some of this. So as we scroll down here, he kind of describes and has a little, I wouldn't say rant, but a little opinion piece on labs and how you should test over labs. But just like the labs we did, he talks about here the 16 labs that the College Board recommends that we do in class. The labs we did are directly based upon these, and he has good facts about what we would know about those relationships, the questions that could be asked related to it, and give sample questions, which are going to be very closely related to the questions I'm asking you. So you'd scroll through this and just take this as a chance to kind of skim, okay, have I ever done something like this? Because on the AP Chem test, you'll see some free response where not necessarily you're designing an experiment, but you're thinking about what data means or error analysis or a process question. So I'm going to highlight this document here, something that's a little bit more general rather than looking at specific labs. And the others two are probably worth your time to read through once, not to try to memorize, but to try to just refresh yourself that those are things that we did or things connected to what we did. So as I scroll through this, we've got all our constants, all our equations. It's good to remember that we'll be given those. But right here, we've got some big ideas. If you've taken other AP classes, especially AP Sciences, maybe Bio, and I know for sure AP Physics 1, there's very specifically a question about designing a lab that's worth a lot of points. That doesn't happen on Chem. We don't have a full question that's just lab-based in terms of design. It's kind of sprinkled throughout the free response. Sometimes it's analysis, sometimes it's looking at graphs. Every now and then it's drawing a graph, although that is less common in Chem than in physics or other classes. And then sometimes it's just analyzing the data. So thinking about this, sometimes we would design an experiment. If we are asked to do that, a key thing is thinking about what are we trying to measure and what calculations would we do. You are very, very rarely asked to explain the calculations, but you want to think about what are the calculations to make sure you get all the right measurements. You might have to think about sample data. You won't have to create it. They would give you a data table. But once again, thinking about, well, how do I do this problem? Most commonly interpreting graphs, and very common to think about the effect of an error. So those are all things that you might see on the AP exam, but very rarely is it all together. So if it's a lab question, it's going to be kind of brief in terms of these. Sometimes they'll ask you for materials. In AP Chem, it's most commonly, if they're asking you for materials, they're asking to make sure you know what piece of glassware is used for what. Burettes and pipettes and graduated cylinders are used to precisely measure volumes. Beakers and flasks are much more for mixing and doing reactions in. So knowing that. For the procedure, it's not always a step by step, but thinking about things like adding enough reactant so we totally collect our precipitate, drying a precipitate, massing our final mass a few times to make sure that it's totally precise. And we see things like that. Rinsing solutions, rinsing burettes. In terms of data, we're thinking about what do we actually measure. So right here is a great example. We can measure mass, we can measure volume. And when we're thinking about temperatures, we measure initial temperatures and final temperatures. We don't measure temperature change. When we're doing a titration, we measure our initial volume and our final volume, not how much was added. In terms of calculations, sometimes you'd be asked to explain that. Sometimes you'd be asked to do it, but much more commonly, you're just going to be thinking about it. If it's a heat experiment, you're thinking Q equals MC delta T. Do I have all the measurements I need to know my mass accurately? Do I have both of my temperatures? If you are drawing a graph, make sure that you're thinking about numbering it well, labeling it well, and looking at where your points go. Or much more commonly, we're interpreting graphs in Chem. With error analysis, be very specific. Is the value too much, too little? Is there no change in it? And sometimes using sample data or made up numbers really help you with that. Titrations are tough because we think, well, if the volume's too big or too small, what does that do to a final calculation? So really kind of walk through the calculation one equation at a time until you know what it's going to do. The most common procedures that they are asking about, maybe not designing, but asking experiments about, are calorimetry. That's where we're thinking about heat, Q, and delta H. I'm not going to read all of this to you, but some really important ideas are listed throughout there. So you can open this up, obviously check it out on your own, but we're thinking about measurements of mass and measurements of temperature, which gives us Q. Q then is divided by our limiting reactant to find our moles of our limiting reactant to get our delta H. And then do remember the sign on this, that if the temperature is going up, it's because it's exothermic, and that's a negative delta H. So a lot of other details here, but those are some of the key ideas. We do titrations all the time. We do those for acid base. We do those for redox. You can actually do them for other types of reactions. But to that end, we need to be, really sure that we're not just saying, well, the pH is doing this or that, because it might be redox or something else. So we've got some terms here. Titrations are used for stoichiometry. So they're mole-mole ratios. And we're thinking about the equivalence point where the moles are equal to one another. Remember, we always rinse our burette. If they talk about not rinsing a burette, then the concentration of that thing is probably going to be lower than it should be because it's going to be watered down or reacted with something else. We drain through the whole thing, including that bottom tip of the burette, so that we rinse that, but also so that we don't have any air bubbles. It's talking about air bubbles here as well. When we are doing all of this, we're also being as precise and careful as possible. And then here we're trying to get moles equal to moles. Most of the time we do this in terms of molarity. So we can do molarity times volume, accounting for our mole ratio. But every now and then we also might think of this in terms of molar mass. We can do a titration starting with a solid in our beaker or flask. So we've got this right here. Do remember that we know our equivalence point is the steepest point and that the half equivalence point is super important. If this is a weak acid or weak base, we know all the things about pKa and pH that help us out there. Gravimetric analysis is a generic term for any time we're thinking about mass, and really it's most common if we're thinking about making a precipitate. So we mix two things together, we make a precipitate, then we have to dry it off. We form the precipitate, we filter the precipitate, we dry the precipitate, and we weigh it. And when it says constant mass, we dry it a few times, and then once that mass stops changing, that's when we know that it's correct. One thing that's important here is whatever ion we're trying to precipitate, we always add more than enough or in excess of the other thing to make sure we have enough. And we've got that described right down there. Determining molar mass can come all sorts of different ways. It could be from a titration, but what we're trying to do is find our moles of our sample and then obviously our mass in grams. So we could think about this in any other ways. So remember, we are calculating this. So what are we measuring and what are we calculating? We also did this with a volatile liquid, or where we took that liquid, we warmed it up in hot water, and it turned into a gas. So we looked at PV equals nRT, the pressure, volume, and temperature to know how many moles. If something is collected over water, and it will specifically say that, and it would also within the problem have to tell you the vapor pressure of water. Remember, we take our measured pressure minus the vapor pressure to get our pressure of just our gas. Colorimetric, spectrophotometric means that we're looking at the color of a solution. We actually did this a couple times. We did it with crystal violet, the purple that went colorless. You did it at home with your Gatorade or food coloring or whatever. And the key idea, we've got some different things here, but the absorbance is directly proportional to the concentration. So we're going to have a nice graph with a nice straight line with the positive slope that tells us as I put more chemical in, the absorbance gets higher. And a lot of times, if you're analyzing an unknown, it just tells you the absorbance. You go across and drop down to estimate or to ballpark what our concentration will be. So we've got a lot of equations here, just kind of things that we saw coming back. With electrochem, since we didn't mention that, a lot of times they'll give you the diagram, but we're showing maybe where the ions are flowing, cations within the salt bridge to the cathode, anions to the anode, and electrons flow from anode to cathode, fat cat. Those are things we might draw. We would also think that the fat cat, the cathode gains mass as we add solid to it. The anode decreases in mass as it dissolves away. Stoichiometry can happen all sorts of different ways. It could be empirical formulas, gravimetric analysis, etc. Acid-base is almost always going to be a titration. Thermo's almost always going to be calorimetry. Qualitative analysis is much less common than it used to be, but that does have to do with reactions and precipitation and solubility. This is when we're thinking about if I'm adding some ions in, they might precipitate with one chemical, but not with another. so we can identify what compound is in there based upon what does precipitate. Our pitfalls are reminding us the difference between a measured value, like an initial mass and a final mass, an initial temperature and a final temperature, an initial pressure or volume and the final, compared to the calculated change in those. Or we might measure the volume of a liquid and use the density to calculate the mass. Those important little steps. We keep heating it until the mass stops changing. We rinse our glassware and with the solution. We dissolve things. When we are making a solution, and there's a question about this on the quiz, we put in some water, we add what we're trying to dissolve, and then we fill to the line of our flask. That's really important. The math on this, it's much less common. You have to do a precise calculation, but we're used to doing calculations. So use those equations. And if there's something we haven't done, there's two things that are important. It's a good chance somebody else didn't do it. We do as many labs as possible for any given year. So keep that in mind. So if it's new to you, it's probably new to a lot of people, but also it's related to something that we've done. There's a super problem is what we call it here, but just like a really long problem that connects a whole bunch of other stuff if you want to check that out. But really just thinking about this and then answering the quiz questions is going to be the key to what you need to know.